the main thing we are talking about is how to evaluate the integrals for a big class of functions. Now look at part 3. In part 3, so maybe you look at question 3. Okay. In question 3, eventually we are going to be able to evaluate the integral for any rational functions. By rational function, I mean a quotient of two polynomials. A quotient of two polynomials, like the integral in question number E, question number C, and so on. Okay, you see the function, the integrand is the quotient of two polynomials, right? The degree of the numerator, every polynomial has a degree. The degree of the numerator is 3. The degree of the denominator is also 3. Okay. Now for this one, I think the same thing. Yeah. Actually, for the B class, eventually we are able to evaluate the integral of any rational function, any quotient of two polynomials. Okay. Now look at some general idea, the general things. Okay. Again, a rational function is defined as the quotient of two polynomials. In this particular case, I'm using p of x to denote the numerator. It's a polynomial. Okay. I'm using q of x to denote the denominator. It's also a polynomial. The first thing we do is to define what we mean by improper rational function. Improper rational function. By improper, we mean the degree of the numerator is greater than or equal to the degree of the denominator. In this case, you do long division. Long division. I'm pretty sure you can remember the term, but you learned that a long time ago. I will show you how to do long division. Okay. Again, the first thing we do is to convert the integral of a improper rational function to something simpler. To review long division, I will use a particular question to show you how to do the long division. Okay. Actually, we are going to see how the long division is going to work for this integral. Okay. Long division. Okay. We are going to evaluate the integral first. Again, when you see the integrand is an improper rational function, then the first thing you do is to do long division. I will integrate the same idea, the idea into the particular question. Okay, we'll do long division first. Long division, I believe you can remember that notation at least. It's something like you divide, now let's say 2 into 9. It's going to be the same thing, right? How to do the division for this case? How do you divide 2 into 9? For whole numbers, you need a quotient, and then eventually you get a remainder, right? So in this case, the quotient you need to think at most how many 2's are in 9. At most how many 2's are in 9? 4. At most 4 2's are in 9. Okay. I told this not a long time ago for math for teachers, I guess. Okay, and then you multiply 2 and 4, you have 8, right? And then you subtract 8 from 9, you have 1. After getting the remainders which is smaller than the divisor, and then you're done. There's a relation between 4 numbers. One number is called the dividend, so this number is the dividend. It's going to be the same thing. Okay, dividend. So this number is divisor. This number is quotient, right? This number is the remainder. What is the relation between the 4 numbers? Dividend, divisor, quotient, and the remainder? I think chat is in teaching program, right? You learn math for teacher. You learned this, so not too long time ago. I'm going to write the relation. Okay, the relation is dividend is always the same thing as is always equal to the divisor times quotient, and then plus the remainder. Okay. If you want to know the meaning using some particular numbers, it's always the same as 9 equals 2 times 4 and then plus 1. Dividend, quotient, divisor, quotient, right? And then the remainder, the same thing. Okay, we'll do the same thing for polynomials. I'm pretty sure you can remember you learned how to do the long division for polynomials, right? On the numerator, the numerator is you treat the numerator of the rational function as the dividend. Remember to include the zero terms. So by that I mean the polynomial in general. Okay, so you have x cubed in here. The coefficient of x cubed is equal to 1. You do not have a number times x squared. It doesn't mean you do not have that term. It means the coefficient of x squared is equal to 0. To perform before doing the long division, I always suggest, it's not super necessary, but I always suggest to include the missing terms. So by that I mean you include the term 0x squared. Still you have a polynomial. You have the term a number times x squared, so just the coefficient is equal to 0. To avoid making mistakes, include the 0 terms. Okay. And then you have a term, so now let's say 1 times x, right? And then plus 0. Okay. Again, include the missing terms, so that when you do the long division, it's going to be easier. And then the divisor, you treat the denominator as the divisor. So later on, we are going to get the quotient and the remainder. Okay. For this one, you just put x minus 1 in here. If you want, you could use brackets. Okay. Perform the long division for polynomials, you need more steps. Okay, you need more steps. Every time you write a number times a power function as a quotient, a number times a power function as a quotient. Okay. So what power function do you need here? You think what power function, what number times a power function times x minus 1, the largest possible power function is in the dividend. Can I say that way? Actually, you want to make 1 times x cubed. You think which power function times a number multiplied by the dividend is equal to something x cubed. I think the power function you need is x squared in here, okay, right? You just line it up, x squared. I need x squared here, so because x squared times x minus 1, you have a polynomial of degree 3. Actually, the coefficient of the product is 1 times x cubed. I think you know what's going on. It's very similar to the number division, right? Okay, and then you multiply x minus 1 and x squared. You have x cubed, right? And then minus, you multiply that polynomial, the dividend and the quotient. So you have minus x squared, right? Again, in the first step, I want to multiply a number times a power function so that the product has the largest power is 3, has that term, okay, has x cubed. And then you want to subtract the product from the given dividend, the same as before. Okay. If you want to write a subtraction notation, you'd better use brackets here, or you write the subtract notation a little bit further. It means you subtract the whole product from the dividend. Okay. You know what I'm doing? So try not to write the subtraction sign too close to this thing to avoid the misunderstanding. It's not negative x cubed. Okay, I still want to use brackets in here. Okay. So the meaning is going to be clear. Your target, after the subtraction, you can reduce the power. You can reduce the degree, You can reduce the degree of the polynomial. Okay. So 0 times x squared minus x squared, right? You'll have positive x squared. It's like subtracting a negative number is equal to positive. You know that, right? The same as number division, you need to move these two terms down. So you'll have plus x in here and then plus 0, right? And then you repeat the same thing. You do the same thing, and then you think what power function you need in here. You want a number times a power function, so that in the product, the first term in the product as a polynomial has x squared, so that in next step you are going to reduce the power again. Okay. Yeah, you have x, right? You need x in here. It's very much like number division actually. And then you multiply x and x minus 1, so you have x squared minus x, right? And then you subtract from this part. Okay, I think this term is 0. You do not have to write 0. And then x minus negative x minus negative x, you have 2x, is that right? I think you have 2x and then plus 0. You cover 0. You are still not done yet. I will tell you when you are done very shortly. We are almost done. Okay. And then the next thing we do, so what number do we need here? So this time we need a number or a polynomial or a power function of x, a number times a power function of x, having the condition that satisfying the condition that you multiply this thing and the dividend. I think you know what you need. So you just need a 2. You want the product of 2 and x minus 1 as the product as a polynomial. The first term is 2x, right? So you know that. So you have 2x minus 2. Eventually you have 2 in here, right? So 2 is coming from 0 minus negative 2. You have 2 in here. Now you are done. Now you are done. In general, when you are done, in general, you have a divisor. Now let's recall the terms. The whole thing here is going to be called a quotient. You have a divisor. This thing is going to be called a remainder. I'm talking about when you finish. Now listen to me. Now remember, when the degree of the remainder is less than the degree of the divisor, then you are done. You are done the long division. I want to repeat. You keep on going when the degree of the remainder is strictly less than the degree of the the degree of the divisor, then you're done. In this particular case, the remainder is 2. We treat a constant as a polynomial with the degree of 0. The degree of the remainder now is 0, right? And then the degree of the degree of the divisor is 1. 0 is less than 1, right? When the degree of the remainder is strictly less than the degree of the divisor, then you're done. After you're done, your quotient is here, your divisor is here, your remainder is here, your dividend is here. Okay. Again, the relation between the 4 numbers, the 4 things, in this particular case, the 4 polynomials, is very comparable to the 4 things in numbers. It's always true that the dividend is equal to the divisor plus quotient, then plus the remainder. Okay. In this particular case, you're going to see how the long division will work for integrating a rational function very shortly. Okay. In this particular case, the divisor, the dividend. Okay. The dividend is. Can I write everything on one page? I'm going to remove that. After the long division, you'll see the dividend. So this time I'm going to omit the 0 terms. X cubed and then plus 3, the dividend, and then plus x, okay. The dividend is equal to the quotient times the divisor. The quotient in this particular case is x squared and then plus x and then plus 2, the quotient, right? The dividend is equal to the quotient and then times the divisor. The divisor is x minus 1, and then plus the remainder. The remainder is 2, right? I believe you can follow me. It's nothing but the dividend is equal to the quotient times divisor and then plus the remainder. So it's true. If you want, you could check. By that I mean you could multiply out the right hand side. You will get the left hand side. Okay. What do we do next? Originally we want to integrate that function, right? We want to integrate, now look at the mouse cursor, that rational function. At this point, you divide 2 sides of the equation by x minus 1, you have the given integrand. Okay. From here, you divide 2 sides of the equation by x minus 1, you have x cubed and then plus x over x minus 1. That is the function we want to integrate, right? After the long division, using the long division, you divide 2 sides of the equation by x minus 1. You have x squared. So do you see this term divided by x minus 1 is actually the quotient of the long division? X squared and then plus x and then plus 2, right? That is actually the quotient. And then plus 2 over x minus 1. Okay, now look at the whole thing. So let's zoom in carefully. I'm going to tell you the idea. After a long division, in all the cases, actually it's true in general, in all cases, the integral of an improper rational function can be converted to a polynomial and then plus a proper rational function. Okay, I want to repeat. After the long division, I'm trying to say why we do the long division. After doing the long division, using the relation between the dividend, quotient, divisor, and the remainder, the integral of an improper rational function can be converted to an integral of a polynomial, and then plus an integral of a rational function, a proper rational function. Okay. You see on the right hand side, you have a polynomial. The underlined is a polynomial, right? And then the double underlined part is a proper rational function, right? So to integrate the given function, all we need is to integrate the polynomial, which is simple, right? And together with and plus the integral of a proper rational function. Both of the integrals on the right hand side are simple. Okay. Okay, now let's finish that. Okay, I will give you the complete solution to that. The polynomial should be super easy to integrate, right? Okay, antiderivative of x squared, you have x cubed over 3, right? And the antiderivative of x, you have x squared over 2. Antiderivative of 2, you have 2x. So did I mention how to integrate something like this? Actually, when the numerator is a constant or 1, when the denominator is a linear function, it's easy to integrate. I will give you the answer, okay, first, and if you want, I can show you why. And the integral of this is equal to natural log of absolute value of x minus 1, and then plus c. Okay, sorry, I forgot a factor of 2. You leave out this 2. Okay. That is the final answer. I don't remember I mentioned it before, but now I want to show you why. That's actually one of the basic forms. If you have an integral like this, can I do x minus a in general? If you have an integral of like this on denominator, if you have a linear function, I told you the answer. So how about I will show you the substitution first, so before we get the answer. Okay, for a integral like that, I'm pretty sure I told you the answer to that before. Okay, but I want to mention it again. For an integral like this, you do not have a handy formula. Actually, okay, we let u be, now let's say x minus a, and then we follow the routine. We compute du, the differential of u. Du is dx. The derivative of x is equal to 1, right? And then the given integral is going to be converted to a new integral of us. I will copy the given one. It's converted to a new integral of us. On denominator you have u. On numerator dx is the same thing as du, right? Now you have now in the as a integral of u, you have the answer to that. Natural log of the absolute value of u, right? And then plus c. Write the answer in terms of a function of x, and then plus c. You have natural log of absolute value of x minus a, and then plus c. I just now you look at two sides of the equation. That's probably something you are going to see over and over again in the future. You do not have to show this work. You just remember this integral is equal to natural log of absolute value of x minus a, and then plus c. Do not forget absolute value notation. Okay. This question is designed to show you how the long division is useful. Okay. Now we only need to concentrate on how to integrate a proper rational function. Right? By proper we mean it's a quotient of two polynomials. By a proper rational function, we mean a quotient of two polynomials in which the degree of the numerator is less than the degree of the denominator, strictly less than. Okay. I think we have seen this. After the long division, any improper rational function can be written as, now look at the cursor, now look at the PDF file. Any improper rational function can be written as a polynomial and then plus a proper rational function. Actually, this R of x is the remainder in general after you do the long division. Okay. So we only need to concentrate on a proper rational function. Does that make sense? If you look at the list of the integrals we are going to evaluate, the integrand in question D is a proper rational function. You see the degree of the numerator is 0. I told you we treat a constant as a polynomial of degree 0. The degree of the denominator is 3, right? That's a proper rational function. And for question A, so maybe my intention is to do question A, but we'll do that later. Okay. For question A, the degree of the numerator is 1. The degree of the denominator is also 1. It's improper, right? To be proper, the degree of the numerator has to be strictly less than the degree of the denominator. For question C, we need to do long division, right? Later on, we'll work on all these questions. But before that, we need some theory. Okay. To handle how to integrate a proper rational function, we need something called partial fraction decomposition. Partial fraction decomposition. So basically, we want to represent a proper rational function in terms of something simpler. Okay. The whole thing is called partial fraction decomposition. After this, we are going to be ready to integrate any rational function. Many cases in the notes, but you do not need to memorize too many cases. I will try to give you a simplified version, of everything in here. Now concentrate. So this thing is not supposed to be too simple. Now concentrate. Okay. How about I'm going to write some step procedures, a simplified version. Okay. It's partial fraction decomposition. The whole procedure is called partial fraction decomposition. Our target is to write a improper rational function to some simpler form, so that each term is going to be simpler to integrate. That's our target. Okay. Steps for partial fraction decomposition for a proper rational function. You could copy it down. Okay. I will give you a simplified version. Now step 1. When you see a proper rational function, of course, if it's improper, you do long division first. Okay. I said for a proper rational function. Now step 1. So what you do is to factor the denominator as far as possible. Factor the denominator as far as possible. The next thing I want you to know, I'm not going to write it down. I will show you the thing. Factor q of x, the denominator, as far as possible. Theoretically, any polynomial can be factored as the product of linear functions and irreducible quadratic functions. By irreducible, we mean the quadratic function cannot be factored any further. Okay. I will show you what I mean. Okay. The term linear functions are simple to understand. So probably I'm going to make some comments on your slide. Okay. Linear functions are a function, now let's say in this form: 2x plus 4, 3x minus 1. These are linear functions. In general, a linear function is in the form of ax plus b, right? That's linear function. We call a function in this form linear function. For some quadratic functions, they cannot be factored any further. Okay, now let me show you a particular case. If you have a quadratic function is a polynomial of degree 2. Okay. If you have a quadratic function, so something like this. So now let's say x squared, and then plus x, and then plus 1. That's a quadratic function. Again, by quadratic function, we mean a polynomial of degree 2, a quadratic function. I will tell you how to check if it's irreducible or not. By irreducible, we mean the quadratic function cannot be factored further, cannot be factored as a number plus a and then plus another number and then plus b. It's never possible. It's never possible. How to determine that? I do not want to write any improper notations in your notes. Okay. How you determine that? You use something called discriminant. The notation for the discriminant is delta, uppercase delta. Okay. You compute uppercase delta. Now let's say for that quadratic function, a value is equal to 1, right? A value is equal to 1. A is the coefficient of x squared. I think the standard form is something like this: a squared and then plus bx and then plus c. I could just talk about the general case. Okay. Any quadratic function can be written in that form. This is kind of the standard form. In the standard form, when I say a, I mean the coefficient of x squared. When I say b, I mean the coefficient of x. When I say c, I mean the constant term. Okay. Now I'm talking about how to determine if the quadratic function is irreducible or not. By irreducible, we mean cannot factor the further, cannot be factored further. Okay. To determine that, you compute something called discriminant. The discriminant of a quadratic function, recall something you learned in high school. You learned that in pre-calculus 11. You learned that. No square root in this case. The discriminant of a polynomial is defined as b squared minus 4ac. Okay, now look at that polynomial. Okay, look at that quadratic function. In this quadratic function, a value is 1. A is the coefficient of x squared. B value is also 1. B is the coefficient of x. And the C value is also 1. I made a nicer number. Okay, I made the numbers nicer. Again, a value is the coefficient of x squared. B value is the coefficient of x. C value is the constant term. Okay. And then to determine if the quadratic function is irreducible or not, you compute the discriminant. Delta is equal to b squared, so in this case 1 squared minus 4ac, 4 times 1 and then times y, right? A, b, and c are 1s. In this particular case, you'll have the discriminant value of negative 3, I think. Negative 3. 1 minus 4, you have negative 3. It's a negative number, right? I haven't told you the condition yet. It's negative. Now remember, this is the case when a polynomial, when a quadratic function, I mean, this is the case when a quadratic function is irreducible. Compute the discriminant. If the discriminant is negative, it's a negative number, then the quadratic function is irreducible, meaning it cannot be factored further. Did I make it clear? And then look at a conclusion. It's probably on this page. Theoretically, you see the discriminant is here, right? Okay, I will tell you a conclusion, okay? The first thing you do is to factor the denominator as far as possible. Theoretically, any polynomial can be factored as a product of linear functions and irreducible quadratic functions. By that I mean if in the factored form of the denominator, if you have a polynomial of degree 3, it's for sure it's possible to factor it further as the product of a linear function and a quadratic function. Okay. And then for all the rest, I'm going to use question 2 to illustrate how to do partial fraction decomposition. Again, the term is called partial fraction decomposition. I think I want to copy the whole question 2. Now look at the question 2, okay? Now look at the question on the screen, on PowerPoint. Anybody want to tell me the... Sorry, I did not copy everything in. I will try again. That's good enough, I think. Okay, now look at the rational function on the screen. Now try to answer my questions, okay? Answer my questions. What is the degree of the numerator? Of course, the whole thing is the quotient of two polynomials. That means the whole thing is a rational function. What is the degree of the numerator? 3. You look at the highest power, right? What is the degree of the denominator? I believe you can guess the degree of the denominator. The degree of the denominator, you imagine you multiply everything out. It's going to be way bigger than 3. I don't know the number. It's probably it's easy to figure out. The degree of one factor is 1, this factor is 2, this factor is 6, right? The degree of that factor is also 6. I don't know the total. The total should be 1 plus 2 plus 6 plus 6. I think it should be more than that. I don't know the number. But I'm trying to tell you the whole thing is a proper rational function. The whole thing is a proper rational function. The degree of the denominator is way more than the degree of the numerator for sure. Okay. Now I will use that particular question to show you how to write the form of the partial fraction decomposition. Of course, the first thing you do is to factor the denominator as far as possible. Now you follow the mouse cursor, my mouse cursor, okay? That's a linear factor. X is a linear function, right? That's x minus 1 is also a linear factor. As far as possible, you probably have 2x minus 1s, right? And then you combine repeating factors using something to some power. In this particular case, you imagine you factor a polynomial as far as possible. You have 2 repeating x minus 1s, and then you write the whole thing as x minus 1 squared. Now, try to answer my next question. Is x squared plus 1 irreducible? Is x squared plus 1, that's a quadratic function, okay? Is x squared plus 1 irreducible? By that I mean, is it possible to factor this quadratic function further? To determine that, you compute the discriminant. I think that's the spelling. Discriminant. You compute. Now let's say delta. Okay, that's b squared minus 4ac. If this number is negative, then this one is irreducible. In this particular case, b value is equal to 0, right? So we have 0 squared minus 4 times 1 and then times 1. It's negative 4. So which means x squared plus 1 is irreducible. The meaning of irreducible is the quadratic function cannot be factored further. And likewise, for the last factor, the stuff inside the brackets is also irreducible. We have seen that, right? Now you see the denominator has been factored as far as possible. Okay. After factoring the denominator as far as possible, then you are ready to write the form for the partial fraction decomposition. Okay. I will complete the step procedures. I will give you some simplified version. Okay. It's not quite step 2. Step 1 is to factor the denominator as far as possible. It's not quite the step 2, but it's just a few cases, probably some cases. Okay. Can I add some more wording? Factor the denominator as far as possible. Then can I just say combine repeating factors. It's something like on denominator only. Okay, if you have a factor like so now let's say 2x minus 2, and then you have x minus 1, and then you have 3x minus 3. In this case, I still want you to combine the repeating factors. From these two terms, you take out 2. From these two terms, you take out 3. 2 times 3 is equal to 6. I believe you can follow me. If you see 3 factors like this, I want you to combine the repeating factors and write everything as 6 times x minus 1, the whole thing cubed. Because essentially, these 3 are 3 repeating factors. So do you see what I mean? When you see 3 things like this, you need to write the whole thing as 6 times x minus 1 cubed. I made some comments. That's what I meant by combine repeating factors. I made some comments already. Okay. After that, I think I only want you to remember 2 cases. I do not even want to use the general number like m or n. We just use some particular factors in this form. Okay. So how about I will talk about the thing a little bit more general. Okay. Okay, one case is for whatever the numerator. At this point, I do not care about the numerator. I'm going to put a question mark in here. Okay. So do you want more cases? Yeah, probably I can give you more cases. Okay, I do not want you to remember too many cases. Okay, I still want to combine. Okay. Whatever on the numerator, as long as on the numerator you have as long as the whole thing is a proper rational function. Now let's look carefully. Okay, so this thing is not too simple. I'm trying to make it clear. Okay. After combining the repeating factors, if you have something like this, if you have now let's say a linear function ax and then plus b, and then times many other things. Many other things cannot be combined with that term. Okay. So do you want to use to the power of m? Okay, I'm not going to use m. I'm going to use a particular number, so like 3. Okay. 3 can be replaced with 4, can be replaced with 5, can be replaced with any whole number. Okay. In this case, in the form of the partial fraction decomposition, if you have a linear function to the power of 3 corresponding to the form of partial fraction decomposition, you have 3 terms. Listen to me carefully. Okay. The first term is going to be a number a1, now let's say over ax plus b to the power of 1, and then corresponding to a linear function to the power of 3. Okay, correspondingly you have 3 terms. The first term is a number a1, the denominator is ax plus b. The second term is now let's say a2, another constant. On denominator you have ax plus b squared, the whole thing squared. I told you corresponding to a linear function to the power of 3, you have 3 terms. Now the third term is a number a3. I'm going to use a3 to denote the third number. On denominator you have ax and then plus b. I mean ax plus b, the whole thing cubed. Of course, there will be many other terms. At this point, you just remember what I'm telling you right now. Very shortly, everything is going to make more sense. Again, I wrote a question mark on top. At this point, the top can be anything. Okay. as long as the whole thing is a proper rational function, then in the form of partial fraction decomposition, if you see a linear function to the power of 3 in the form of partial fraction decomposition, you have 3 terms like this. Okay, I'm going to now I want to give you the general form. Okay, I want to replace this 3 with any number n. If you have a linear function to the power of n, so correspondingly you have n terms. Okay. Okay. On numerator you have a number. I believe you can imagine the pattern. Okay. The last term is going to be ax plus b to the power of n. On numerator you have an. At this point we do not know the constant. We just know there must be some constants. So very shortly I'm going to tell you how to determine the constants. After you learn how to determine the constants, then you'll know how to integrate the function. You just remember that for now. Okay, everything will make more sense very shortly. And then you plus many more terms. Of course, there will be many more terms. At this point, I want you to remember only one thing. I want to emphasize only one thing. Okay. For each term, the numerator is a number, a constant, in the form of partial fraction decomposition. Okay. So just copy it down first. So everything will make more sense very shortly. Okay. I still do not care about the numerator. The second case. Only the second case. I will say that the third step. Okay. The second case is if you have a irreducible quadratic factor. The general form is ax squared, and then plus bx, and then plus c to any power. Can I say to the power of? Now let's start from to the power of 3 first. Okay, to the power of 3 first. So very shortly, I'm going to replace 3 with any number n or m. It doesn't matter. And of course, there will be many other factors on denominator. Okay. Now I'm trying to tell you in the form of partial fraction decomposition, if you have a irreducible quadratic function to the power of 3, and then in the form of partial fraction decomposition, there will be 3 terms. I will tell you the form of the 3 terms. Okay. I believe now you can guess the denominators. The first one is ax squared, and then plus bx, and then plus c. And then the second term is going to be ax squared, and then plus bx, and then plus c, the whole thing squared. The third term is going to be comparable to the case in step 2. Okay. And then plus c to the power of 3. Of course, there will be many other terms. Now remember the numerators. The form of the numerators are different. So this time, if the denominator are irreducible quadratic factor to some power, then the numerator must be linear functions. For the first term, so can I just say d1x and then plus a, b, c, d, e1. For the second term, I'll say d2x and then plus e2. d1, e1, d2, e2 are also numbers. I'm trying to say the numerators are linear functions. So this is the case when on denominator, when you see a irreducible quadratic factor to the power of 3, correspondingly in the form of partial fraction decomposition, you have 3 terms. And of course, I can replace this 3 with any other number. Can I talk about the general form now? You can replace the power 3 with any power n, okay? And then you just need to give a pattern. Now you just need to replace all the little 3's with the n's. Okay, so just copy it down. I know at this point you are not fully getting it yet. I will use a particular question to show you the meaning. Again, I did not want to include too many cases. I did not want you to memorize too many cases. Actually, there are only 2 cases. There are only 2 cases I want you to remember. The only case is when the denominator, you just remember when on the denominator, after you factor as far as possible, if you see a linear function to any power, to the power of n, correspondingly you have n terms. One other thing you need to remember is all the numerators are numbers. Another case is when the denominator is a irreducible quadratic function to some power, to the power of n. Correspondingly, you have n terms. It's easy to get to remember the form of the n terms. And then I wanted to emphasize, I want you to remember the numerators are linear functions. Okay, I know you are not fully getting it yet. Now I'm going to make my point using that question. After this question, you will know everything. Okay. Now the question is to ask us to write the form of partial fraction decomposition. Now follow the mouse cursor. Now you look at the mouse cursor, okay? The first factor on the denominator, again, you imagine you have an improper rational function. We factored the denominator as far as possible. Now follow the mouse cursor, okay? The first factor is a linear function. The linear function is actually in the form of ax plus b, right? So just a value is 1, b value is 0. That's a linear factor. Okay. Corresponding to the linear factor to the power of 1 in the form of the partial fraction decomposition, you have 1 term. So that makes sense? For the linear function to the power of 1 in the form of the partial fraction decomposition, you have 1 term. The 1 term is given by, you want to tell me the denominator? No, you look at your notes, or you look at the general thing. If you have a linear function to the power of 1, you have 1 term. The denominator is the linear factor, right? Then the numerator is a number, a constant, corresponding to that underlined term. In the form of partial fraction decomposition, you have 1 term. the denominator is x, the numerator is a number. Can I just use a to denote the number? We do not know the number yet, so later on I'm going to tell you how to determine the number. After determining the number, you will know how to integrate the function. I will give an underline here corresponding to that factor, the underlined factor. You have an underlined term. So we're done that term. Okay. For the next term, I'm going to double underline the next term. I mean the next factor. I'm double underlining the next factor. The next factor is a linear function squared, a linear function to the power of 2, right? If you factor the denominator as far as possible, after that, if you see a linear function squared, correspondingly in the form of the partial fraction decomposition, you have how many terms? You have 2 terms, right? You have 2 terms. The 2 terms are going to be x minus 1 on denominator, and then the next term is going to be x minus 1 squared, right? Again, corresponding to the double underlined term, x minus 1, the whole thing squared. In the form of partial fraction decomposition, you have 2 terms. I will double underline the 2 terms to indicate it's corresponding to the second factor in the denominator. Okay. So just remember the numerator, when the denominator is a linear function or linear function squared or linear function to whatever power in the form of the partial fraction decomposition, the numerator are constants. The numerators are constants. Okay. Can I use b1 to denote the first number? Can I use b2 to denote the second number? Right. We are not done partial fraction decomposition yet. Do I still want to triple underline? I will change the color. Can I change the color? I'll change the color. Okay. Oh. What color do you want? Now let's use this color, orange. I think that's orange. Sorry, I'm a little colorblind. That's why I have to learn math. I cannot do chemistry. I cannot do biology. Okay. I will underline the next factor using orange, single underline. Okay, that's a irreducible quadratic factor to the power of 3. That's a irreducible quadratic factor to the power of 3. And then in the form of the partial fraction decomposition, you look at their notes. Okay, you have 3 terms. So do you want to try to write the 3 terms by looking at your notes? I think we can do it together. Okay. The numerator is always linear functions. I used a b, so can I use cd for this? For the numerator, I'm going to use cx, c and d for the numbers. So maybe cx, c1x and then plus d1, right? Corresponding to x squared plus 1 to the power of 1, and then c2x and then plus d2, and then c3x and then plus d3. And of course the choice of the notations are different. You just need to know a whatever, b whatever, c whatever, d whatever are numbers. So later on, we're going to learn how to determine these numbers. We're not done partial fraction decomposition yet. I believe for the orange underlined, the last factor. Now for the last factor, so correspondingly we have 3 more terms. I guess for the last thing I can run a little bit faster, right? You got the idea already. Okay. We have 3 more terms corresponding to the irreducible quadratic factor x squared plus x plus 1 cubed. Correspondingly, you have 3 terms. Okay, you have x squared and then plus x and then plus 1 to the power of 1. Now I have to use e and f and so on. Okay, so maybe e1x and then plus f1 and then plus, so now let's say x squared and then plus x and plus 1 and then the whole thing squared, e2x and then plus 2, f2 I mean. And then the last term, so maybe x squared and then plus x and then plus 1 cubed, I'm going to e3x and then plus f3. Now we are done what we call the form of the partial fraction decomposition. The form of partial fraction decomposition. I will go back to yellow color. The yellow pen color. Probably you can see better for yellow. Or do you want white? I think I can try white even. Yeah, probably white is okay. Probably you can see white better. I could use white earlier. Okay. I will try white for a little while. Okay, now the whole idea I want to mention. Okay. Again, the whole thing is called partial fraction decomposition. Partial fraction decomposition. Okay. In general, you see it's very hard to integrate the left-hand side. So there's no way for you to integrate the left-hand side. You do not have any handy things. But if you rewrite, as long as you can determine the numbers, determine the constants, then instead of integrating the left-hand side, you know how to integrate the first term. You know how to integrate the second term. Actually, integrating all the terms will become simple. People design partial fraction decomposition thing, so just to make the integration of any rational function simpler. So that's the whole idea. Of course, so before that we have to talk about how to determine the numbers, how to determine all these numbers. Okay. But the main thing is to remember the form of partial fraction decomposition for a proper rational function. Okay. If you see a rational function is improper, the first thing you have to do is to do a long division. Okay. You know how the partial fraction thing will work. I hope you can see better if I have white on black. Okay, now I'm going to follow the step procedures. Okay. So step 1 is to factor the denominator as far as possible. Again, the whole thing is the integrand is a rational function, right? Actually, it's a proper rational function. The degree of the numerator is equal to 0. The degree of the denominator is 2, so it's proper. Okay. Whenever the degree of the numerator is less than the degree of the denominator, it's proper rational function. The first thing we do is to factor the denominator as far as possible. This is simple, right? X squared minus 4, we factor the denominator as far as possible. Okay. Factor x minus 4 as x minus 2 times x plus 2. All of you guys know that. Okay. The second thing we do is to write the form of partial fraction decomposition for the improper rational function. You have 1 x squared minus 4. And probably I want to use the factored form. I will check if you got the idea, if you got the partial fraction decomposition theme. Anybody want to tell me how many terms in the form of partial fraction decomposition? I'm repeating my question. How many terms are there in the form of partial fraction decomposition? The denominator is factored as the product of two linear functions. Two terms. Yeah, two terms. Corresponding to each term, you have corresponding to each factor, you have one term, right? So the form of the partial fraction decomposition is going to be the following. It's going to be the following. Okay. One factor is x minus 2, the single underlined term. You have x minus 2 in here. It's x minus 2 to the power of 1. You just have one term, right? X minus 2 to the power of 1. You just have one term. When the denominator is a linear function, the numerator is a number. Remember, when denominator is a linear function, the numerator is a number. When denominator is irreducible quadratic factor, the numerator is a linear function. Okay. So in this case, so because I need only two numbers, I just use A and B. Okay. I use A for the number. Okay. And likewise, in the form of partial fraction decomposition, you have another factor on the left hand side, on denominator, I mean, okay, x plus 2, right? Correspondingly, for the numerator, you have another number, b. I want to repeat the idea I mentioned earlier. Now, for the integral, we want to integrate the left hand side. As long as we can determine the numbers, then the two terms on the right hand side are easy to integrate. You see that? We're going to complete the solution soon, but that's the idea. In terms of integration, the right hand side is much easier as long as we can determine the constants, right? Now in the next step, actually our job in next step is to determine the constants. Okay. In step 3, we're going to determine the numbers. A simple question showing you all the components involved in integrating a rational function, a proper rational function. Okay. To determine the numbers, to determine the constants, you compute the right hand side. You treat these two terms as two fractions. You just perform fraction addition. Okay. I think all of you guys know that. I will do that in one step. Okay. If you cannot follow me on this, you could be can I just do that in one step? I will just do that in one step. Okay. To add two fractions, you need a common denominator. After getting common denominators, okay, I will do this. After getting common denominators, all we need is to add the numerators, right? I think on the numerator you have a times x minus x plus 2, and then plus b times x minus 2. Right. Any questions on that? I think all of you guys know this. Again, in steps 3, our job is to determine the numbers. As long as we can get the numbers, then the integral of the right hand side, this will be simple. Okay. At this point, you could there are many ways to determine the numbers. Actually, you could you could multiply out the right hand side, and then you compare the coefficients, and then you solve a system of a and b. That's one possible way to do, but I'm not using that way. Okay, I will tell you one other way. Okay, after getting the right hand side, you see for two fractions, for two rational functions, they have with the same denominator. The two numerators, they have to be the same. So that makes sense? We compare the two numerators. We have can switch the side. We have a times x plus 2 and then plus b times x minus 2 equals 1. We can use that equation to determine the numbers. Right. Now follow me. Now I'm not going to talk about the tedious way. The tedious way is probably a little bit more rigorous. But I'm going to talk about a simple way, a simpler way. Okay? A simpler way is to use, now remember, we can use some particular values of x to determine a and b. In general, we can use some particular values of x to determine the numbers. Okay, so tell me what values you want to use to determine a. So basically, you just need to realize some values of x will make one term 0. Which value of x will make the second term 0? X value of 2 will make the second term 0. Yeah, I think Chad told me two values, negative 2 and 2. Right. Again, we use some particular values of x to determine the numbers a and b, the constants a and b. So by that we mean we set x value to be 2, and then the equation will become x value of 2, the second term is gone, right? 0 times b, the second term is gone. The first term will become 4a. So do you see 2 plus 2 is 4? 4a is equal to 1, right? The right hand side is a constant function, it's always 1. This will give you the value of a. So do you see a value is 1/4? Right? And the x value of negative 2, I believe, will determine the value of b. Likewise, you let x value be be negative 2, right? Be negative 2. Full stop in here. And then the equation becomes negative 4b. So do you see how that comes from? X value of negative 2, the first term is gone, is 0. The negative 2 minus 2 is negative 4. That's why I have negative 4b, right? Negative 4b equals 1. The right hand side is always 1. Actually, the right hand side is a constant function of 1, right? That's why we have b value of negative 1/4. Now go back to step 2. You have seen the value of a, you have seen the value of b. The value of a is 1/4, the value of b is negative 1/4. Right. Now using the form of partial fraction decomposition. Now you'll see why we need the form of partial fraction decomposition. Now using the form of the partial fraction decomposition, you have x minus 2 times x plus 2. 1 over that is equal to, can I just leave 1/4? Okay. Actually, it doesn't matter. I just write a value is 1/4. So the first term, it becomes 1/4 times 1 over x minus 2. And then minus b is negative 1/4. Okay. You have minus 1/4 1 over x plus 2. Is that right? Now we are ready to evaluate the given integral. Okay, the given integral now is all we need is to evaluate the integral for the right hand side is the integral of, now let's say, can I leave out 1/4? I'm going to take 1/4 out of the integration notation. Now all we need is to evaluate the integral of x minus 2 minus 1 over x plus 2. We're ready to have the final answer. The final answer is going to be 1/4 natural log of absolute value of x minus 2 using the integral I told you at the beginning, right? Minus natural log of absolute value of x plus 2 and then plus c. Okay, so that's how the partial fraction decomposition will work. You see, it's hard to integrate the left hand side, but if you get the form of the partial fraction decomposition, and if you know how to determine the constants, if you know how to determine the numbers, and then the integral is easy to compute. I mean, the integral on the right hand side is easy to compute. So that's the whole idea. Okay. Actually, using the same idea, you can now it's possible for you guys to integrate any rational function, any quotient of two polynomials. Okay. Any questions on this? Actually, in many cases, determining the constants is a little weird. In many cases, it's not. It could be a little tedious. I mean, but the main thing is here. The main thing is partial fraction decomposition. The main thing. After writing the form of partial fraction decomposition, it's always possible to determine the constants. Okay, now let's work on a little bit more complicated question, and then now I want to do question D. Okay. Actually, your midterm I think is coming soon. I will give you some details on so what day is today? Yeah, today is Wednesday. On Monday I'm going to tell you the details. Probably I have time to do some review. I'm not 100% sure yet. I will give you some details on Monday. Okay. I think we are losing a class for Family Day. When I see this question, I remember midterm. You know what I mean. There's a question on midterm very similar to that, or some alternative form. Okay, I will go over that. Okay. On the assignment, you are going to see a question like that too. So very similar to that. I will give you a detailed solution to that. The same idea as before. Factor the denominator as far as possible. Okay. But before that, you have to convince yourself the integrand is indeed a proper rational function. I said again, you have to make sure the integrand is indeed a proper rational function. Otherwise, you have to do long division. Okay. Denominator, we factor the denominator as far as possible. You have x cubed and then plus 4x as far as possible. If you have a polynomial of degree 3, it's for sure it can be factored. You take out a common factor of x, right? And then you have x squared plus 4. x squared plus 4 cannot be factored further. You can check. So I'm talking about the underlined x squared plus 4 only, the quadratic factor. Okay. For this one, a value is equal to 1, b value is equal to 0, and c value is equal to 4. And then you compare you compute b squared minus 4ac. b squared minus 4ac. I think you have negative 4, right? Which is a negative number. Discriminant is negative. It means the factor is irreducible. There's no way to factor further. So that's as far as possible already. And then our job is to write the form of partial fraction decomposition. The given integrand 1 over x cubed plus 4x. So have you realized what we are doing? Actually, the rational function, the quotient of two polynomials, is a very huge class of functions, right? Very big class of functions. Now, but after learning the partial fraction decomposition thing, we can handle the integration of the very huge class of functions. So does that make sense? Okay, you have okay, the form of partial fraction decomposition. Sorry, I should have used the factor form in here. I will do again. How many terms in the... Can you try to answer my question? How many terms are there in the form of partial fraction decomposition? Two terms again, right? Two terms again. You have a linear factor, single underlined. You know that it's going to be a over x. Corresponding to a linear factor x, you have a over x. Okay. Corresponding to the irreducible quadratic factor x squared plus 4, you have x squared plus 4 on denominator. Do not forget the numerator. Anybody want to tell me, anybody want to suggest a notation for the numerator? So please, anybody suggest some notations for numerators?
bx minus c.
Yeah, bx minus c. I'm just checking if you remember the numerator, it has to be a linear function. Okay, bx plus c is good. Okay, so do not use a single number. The numerator corresponding to a irreducible quadratic factor, the numerator has to be a linear function. bx plus c is good. Okay. You know the next job. After you get this right, you know that the next job is to determine a, b, and c. The next thing is to determine the numbers, right? In step 3. I like this question so because it probably has everything I want to check. You know it has linear factor. You know it has irreducible quadratic factor, right? But irreducible quadratic factor to any higher power, the thing is going to be way more complicated when determining the constants. Okay, the next thing is we're going to do is to determine the constant. Okay, 1 over x times x squared plus 4 on the left hand side. Okay, now what are we doing? We're going to compute the fraction. Okay, we need a common denominator. Common denominator is x times x squared plus 4. Right. And then the numerator, if you want, you can do this in multiple steps, but the numerator is going to be a times x squared plus 4, and then plus x times bx plus c. I think I got this right. Okay. Again, to determine the constants, you compute the right-hand side, something like adding fractions. More precisely, add rational functions. You write the whole thing as one rational function. So you have two rational functions with the same denominator. The two numerators have to be the same, right? Have to be equal. So you have a times x squared plus 4, and then plus x times bx plus c equals 1. Again, it's possible to use some particular numbers to determine the I want you to use some particular values of x to determine the constants. Anybody see what x value you want to use to determine a? You need one particular value of x to determine a. So this one should be 0. X value of 0 will give you the value of a. Okay. So we let x value be 0, and then the equation will become becomes 4a. You just think 0 will make the whole second term 0, right? You have 4a equals 1, which means a value is 1/4. So do you see that? A value is 1/4. And then to determine b and c is a little weird. So this time, okay. After getting a value of 1/4, the equation becomes I'm going to squeeze it here. The equation becomes a value now is 1/4. 1/4 times x squared plus 4, and then plus x bx plus c is equal to 1. So how about I'm going to show you what numbers we chose. Or do you want to guess what numbers we chose to determine b and c? We use x value of 1 and -1 to determine b and c. Okay. Of course, it's hard to guess. I just knew it. -4 is not good. So -4 is not good. If you use x value of -4 squared is going to be 16. It cannot. Actually, this term is never be 0. And look at the cursor. This term is x squared and then plus 4. It's always positive. It's always greater than or equal to 4 actually, because x squared is always non-negative, right? Cannot be negative. And then we use x value of 1 and x value of -1. Okay. I will show you what's going on. Okay. X value of 1. We set x value to be 1. And then I will do this a little slower, okay? Now look at the mouse cursor. If we set x value to be 1, the first term becomes 5/4. So that makes sense. 1 squared is 1. 5/4. 5/4, and then plus x value of 1. X value is 1. 1 times bx plus c will become 1b plus c equals 1, right? from here you have b plus c equals negative 1/4, I think. 1 minus 5/4, I think you have negative 1/4. And then we use x value of negative 1. And then you have x value of negative 1. You plug negative 1 into that equation. Okay, now look at the cursor. Into that equation. I think you also have 5/4. Negative 1 squared is 1. Negative 1, the whole thing squared is 1. And then plus x value is negative 1. Okay. Do you have b minus c? I think you have b minus c, right? X value is negative 1. Negative 1. You just replace x with negative 1. Negative 1 times b times negative 1 plus c. I think you have b minus c, the whole thing. Is equal to, the right hand side is always 1, right? This will give you b minus c is equal to negative 1/4. Is that right? I hope it's not too messy. Okay, so you have two. Now look at these two equations. B plus c is negative 1/4. B minus c is negative 1/4. From these two equations, you can solve these two equations for b and c. You have a linear system for the people in linear algebra, right? You have a linear system. I will put them together, okay? So you have a system. B plus c is equal to negative 1/4, and b minus c also equal to 1/4. From the system, you can solve the system for b and c. Anybody want to tell me b and c? What are b's? What are c's? You add the two equations, you have 2b equals 2 of negative 1/4. So this will give you b value. This will give you b value is 1/4. It's negative 1/4, I think, right? And c value has to be 0. So do you see that? I think all of you guys know how to solve a system like this. You add these two equations, you have 2b, right, equals 2 times 1/4. So 1b is 1/4. And then you plug b value of negative 1/4 into any of the two equations. You have c value of 0. I think I got this right. Now we got all the numbers, right? We have all the constants now. Now you go back to step 2. Now look at the form of partial fraction decomposition in step 2. Now in step 2 we have 1 over x times x squared plus 4. I know this question, the solution to the question is a little bit long, but I want to show you a case which include everything, at least one irreducible quadratic function case. Okay. A value, I think a value is 1/4. You have 1 over 4x, right? A value is 1/4. B value is negative 1/4. C value is 0. Now you look at here. I think c value is 0. It will give you a negative minus. On numerator you have x. On denominator you have x squared plus 4. Probably I missed 1/4. Can I write 1/4 like that? You could use some brackets. So, but I was trying to write minus 1/4 of the whole fraction. I think it's okay. Do we know how to integrate the integral? I think you know how to integrate 1 over x. And then for the other integral, I'm going to do it separately. Okay. Now for the integral of x over x squared plus 4. Actually, it's a pretty typical form for using something you learned before, the substitution rule. So anybody want to tell me how to choose u? The substitution? We let u be, so please. X squared plus 4. You'll see what's going on. Okay. You compute du. Du is 2x and then plus dx. So do you see that box in here? So that's how it works, right? So the equation for the box, you have half of du, right? So this integral as a new integral of u, is going to be the denominator. I think you have u, the numerator, the whole thing in the box, you have 1/2 of du.
Sir, you forgot about the negative 1/4.
Yeah, no. But I'm talking about that integral only. So later on, for the original question, I'm going to include 1/4. Does that make sense? For this integral only. For this one, I think it's half of. Now we have a handy formula for this. Half of natural log of absolute value of u, right? And then plus c. In terms of x, it's going to be half of natural log of absolute value of, okay. X is, u is x squared plus 4. And then plus c. Anybody want to tell me why I can get rid of the absolute value notation? In the last step, I did not include the absolute value notation for a reason.
Is anything squared positive?
Yeah, x squared plus 4 is always positive. Absolute value of x, a positive number, is the same thing. That's why in this case I can get rid of the absolute value notation. So that makes sense. Now remember, this is half of natural log of x squared plus 4. Okay, now we are ready to go back to this. Originally we wanted to integrate that, right? Now all we need is to integrate that. And negative 1/4 of that. Now look at the integral of the first term. The integral of the first term. Okay. I think I told you before, it's actually 1/4 of natural log of absolute value of x. I'm talking about that term. Okay. Now the integral of 1/4 of the integral we just did. You combine the two factors 1/4 and 1/2. You have 1/8. Why it's not letting me turn the page? Oh yeah, natural log of x squared and then plus 4 and then plus c.